various space telescopes that have orbited our Earth and peered into deep space are well known, but not many people may ever have heard of a telescope attached to a balloon. ASTHROS is a new NASA mission that will carry a 2.5 metre telescope into the stratosphere, attached to a helium-filled balloon. Once deployed, the telescope will use infrared vision to unlock the secrets of star formation in our galaxy. I spoke to Jose Siles, project manager of the ASTHROS mission, to find out more.
So my name is Jose Siles. I'm an engineer at JPL. Now I'm the project manager and technical lead of the ASTHROS mission, but my background is also in designing instrumentation for some millimeter wave receivers or the far infrared. So I've been developing instruments for astrophysics, planetary science, and earth science.
This ASTHROS mission is really interesting. How did the mission come about, and how did you get involved in it?
Well, ASTHROS is a far infrared mission to study star formation, and more specifically at some millimeter wave range, which is very important because I don't know if you're familiar with COBE, a previous NASA mission, but that mission discovered that 50% of the luminosity since the Big Bang lies in this frequency range. In fact, most of key tracers of star forming are in this range. So it's widely accepted that the stars play a key role in the evolution of galaxies, right? And yet galactic evolution remains one of the biggest mysteries in astrophysics. So we like to see galaxies are living entities where the interstellar dust and gas collapse to form stars, and then the planetary systems, and eventually these stars die. And for example, with these massive explosions that we call supernovas, and all the material is ejected back to the interstellar medium, and this cycle repeats over and over. But in fact, these supernovas, together with the stellar winds and other stellar feedback processes, reshape and redistribute this gas, changing the distribution of energies. So this stellar feedback somehow regulates the star-forming processes, because otherwise what we know is that all the material will have collapsed into stars long time ago, and no new stars will form. So the model says that with no stellar feedback, that efficiency of star formation will be close to 100%, but we know that actually is a very inefficient process. So in order to understand how this stellar feedback regulates star formation, we need to obtain high spectral resolution 3D maps of this ionized gas. And with 3D maps, I mean not only spatial maps, but also maps in velocities. We need to understand how this gas is moving in that three-dimensional space. And the best proof of that is the ratio between two nitrogen lines that are 122 and 205 microns, ionized nitrogen, in fact. So we are observing the molecular emission of this gas and using the Doppler shift of these emissions to derive the velocities and also separate contributions from different molecular clouds on our line of sight. So we want to see these emissions, but also where they are coming from and in which particular molecular cloud are created. For example, Herschel-Pax was able to look at these emissions, but simultaneously, but not with enough high spectral resolution. So unfortunately, these emissions are blocked by the water vapor on Earth. So we need to be in space or very close to space to see them. And the latter is, of course, accessible with balloons at a much lower cost than a space mission and much faster. So that's why we have ASTHROS now. We want to look at the missions in a fast and low-cost way to somehow complement previous missions like Herschel in this case.
The idea of attaching a telescope to what is essentially a balloon might seem quite sort of rudimentary to a lot of people. Has this technique been done before?
Oh yeah, balloon missions are not new, in fact. If we count all kind of scientific missions to date, there are thousands of them. I don't want to be wrong with the number, but I think that we have had even more than 10,000 missions, so it's a huge number. We can even go back all the way to 1912, and back then Victor Hess took a hot air balloon and wanted to do some experiments measuring radiation as a function of altitude. And that's an amazing project because of that, he discovered the cosmic rays, and he ended up winning the Nobel Prize in 1936 because of a mission done with a balloon more than 100 years ago. And more related to ASTHROS, of course, we flew in 2006 as well a much smaller telescope that was around 0.8 meter diameter, also for star formation that we call a stratospheric terahertz observatory, to analyze some of the emissions also in star-forming regions. ASTHROS is, in terms of collective area of the antenna, is 9 times larger, so it's 2.5 meter diameter versus 0.8 meters. And ASTHROS also has receivers that allow us to capture these nitrogen emissions, or these two lines that STO2, in this mission that we did in 2016, didn't have. So they do sound rather rudimentary, to be fair with you, because it's probably the oldest technology, the oldest flight technology that we know, right? But they have improved so much in the recent years or in the last decades that now you can send a cutting-edge telescope with the newest technology to the stratosphere to do amazing science. So that really makes it very, very exciting.
So whereabouts will the telescope actually be situated? Like how high above the Earth? And I assume it won't be orbiting Earth. Like a space telescope. Will it? How do you sort of control where it goes?
So you're right, we are not orbiting Earth, but we are orbiting Antarctica. So what we're doing is take advantage of these air currents that we call the Antarctic vortex that forms in the Antarctic summer, which consists in a flow or a pattern of currents that are circulated around Antarctica, around the continent. And that's set up for around 4 weeks. So what we want is to go there and launch our balloon when this happens. So during 4 weeks, the balloon can just go around the continent at 40 kilometers. And that's roughly 4 times the altitude that a commercial airplane flies. And during those 4 weeks, do the observations. And then when, this pattern disappears, we just tear the balloon apart and land it using a parachute and just go back or go out there and recover it.
So is the balloon sort of high enough to get beyond the blurring effect of Earth's atmosphere? Does it actually go that high?
Yeah, so I was saying, of course, that one of the problems with these emissions they want to observe, in frequency, we're talking about 1.5 terahertz to 2.7 terahertz. So our cell phone works around 1 gigahertz, so it's much, much higher frequency. And these emissions, they are totally blocked by the Earth's atmosphere. That's also one reason why, especially one of these lines that we want to observe haven't been observed before, because you cannot do it with ground telescope. And the technology is so new that it was not available before in some missions like Herschel. So we know that at 30 kilometers or above 30 kilometers, we are over 99% of the atmosphere at that point. So at that point, our reception of these signals is pretty good. We are flying at 40 kilometers, so it's 10 kilometers above that point that I was mentioning. And so that allows us really to get the science that we want to get. And we can go that high because, of course, we are using a huge balloon. This balloon is 150-meter diameter. It's a perfect sphere when it goes to altitude. So you can imagine how massive this is. It has 40 million cubic feet of helium gas. And that's pretty much that for the weight of our payload. 40 kilometers is the lift we get. So we don't have any risk to go even higher. We would love to go as high as possible, of course, but 40 kilometers is kind of the limit for the weight of our radio telescope. So that's the limit in lift that balloon, the size of the balloon can give you. But it's enough for our science.
How do you actually control the balloon and stop it from just going higher and higher and eventually going into space and just drifting away from Earth?
So the altitude, as I said, we take whatever we can get, right? The higher, the better. But the size of the balloon, the amount of helium that goes into the balloon is that gives you the maximum altitude. So it's a trade-off between the size of the balloon and the payload. You could go a little bit higher, but at that point, the atmosphere is so weak that you just cannot get a lot of lift. So 40 kilometers for us is the limit. We're talking about the ASTHROS is around 5,500 pounds. So with that weight, you cannot really go higher than that. So that's how somehow we control the altitude. And of course, we have some ballast in the balloon, like you will do in a hot air balloon. So that allows you to adjust a little bit the altitude when you are flying. So as you said in the beginning, it's like old technology, right? Applied to very cutting edge telescopes.
Yeah, definitely. There is something quite old worldly about it, isn't it? As you said, you can kind of trace this sort of method going back to the early 20th century. Are there any kind of particular dangers of a balloon being that high up? Is there any danger of it being hit by micrometeorites or anything like that?
Well, I'm not an expert on that, but I know that the atmospheric entry point is around 100 kilometers in altitude. So we're flying at 40 kilometers. So you would expect that at that altitude, any micrometeorite has been pretty much disintegrated by the atmospheric entry, or during the atmospheric entry. In fact, I cannot remember any balloon mission that has been had issues with that. Now, if we're talking about dangers, of course, well, I wouldn't call this a danger, but one of the issues, as I said before, is that we're trying to surf the currents around the continent. And we cannot control that. We cannot control where we're going. You said that before. So if that wind pattern disappears, we could start drifting off continent. And at that point, we, of course, have the risk of losing the payload. So we'll have to break the balloon or terminate the mission at that point and land over the continent while we are still flying over the continent. And by the way, you were asking as well, how do we control it? Yeah, we cannot control it, but we can point at any time where we want to point. So we have reaction wheels, and we have elevation drives, and we have star cameras. So even if we cannot control the position over the continent, we can very precisely control the pointing and even send the data back, the scientific data back in real time, so the scientists can start doing their science. Now, coming back again to the dangers, for me, the most or the highest danger is the launch. Because in the launch, you have this huge balloon with the radio telescope hanging 900 feet below. So there's a huge or a large cable connecting the balloon with the gondola. So the winds have to be perfectly calm. You cannot have winds here because those stresses can basically tear the balloon apart. So that's a very stressing moment until you see that climbing and everything is fine. You have to be very careful with the moment that you decide to release the balloon. And then during the ascent, you're going through all the atmosphere. That means that you're going to go from temperatures in Antarctica, let's say between -10 and 0 Celsius at that moment of the year, all the way to -60 Celsius when you hit the tropopause, and then back up again to, let's say, between -10 and 10 Celsius when you are up there outside of the atmosphere into the stratosphere. So the instruments have to survive all those conditions, not only in net temperature, but also in pressure, because up there we are pretty much in space conditions or very close to space conditions. So the pressure is very low. We're going from sea level pressure to around 0.3 to 3 millibar. So all the instruments have to be designed as well to withstand those pressures.
Yes, I was also reading that the telescope, because it's an infrared telescope, it has to have a cooling system, and it has this quite an interesting way of keeping its mechanics cool. Yeah, that's actually one of the new things, electrical cryocoolers are not new, but they are new for balloons. So in other missions, we have been flying cryogenic liquid helium to maintain everything cool. So we have, for this mission, superconducting receivers. They're bolometers, and because they are superconducting, they have to operate at between 4 and 6 Kelvin, very close to the absolute zero, which means that we need to carry something on board to keep them cold during the entire mission. As I said, you can fly a dewar full of liquid helium, as we have done in the past. But the problem with that is that it's heavy, not because of the helium is heavy, just because the dewar itself is very heavy. You need a lot of liters of helium for the mission. The other problem that it has is when you run out of helium, you're done. You cannot keep observing because at that point, the receivers are no longer working. That, for example, is what happened with Herschel, the space mission. It lasted for 3 years because it's the time that the amount of time that the helium lasted. So what we're doing here is to use a cryogenic cooler, electrical cryogenic cooler that uses electricity to keep the devices cold. So we don't depend on the amount of liquid helium on board anymore. So in principle, we could keep flying, and we are not limited by the liquid helium. So, of course, for ASTHROS, we're just planning to fly 28 days because it's what the wind pattern allow us to do. But to pave the way for future space missions in the far infrared, we want to test this technology because then it will allow us to go to space and keep operating the mission for many years without issues. Yeah, it's really interesting what you were saying about the conditions having to be just right. So does that mean that there's quite a long launch window? And do you actually go out to Antarctica and kind of wait and have to wait there until the mission's launched?
Well, that's one of the most exciting and also challenging part of the mission because, you're working on this telescope for 3 or 4 years until you put it together. You develop the technology, you put it together, you test it in the US first. And then you have to, and that happens for us when we have everything working and tested in the summer of 2023, right? And we're planning to launch in December 2023. So we have a telescope working in summer 2023 that now we have to take completely apart, put it in boxes, and send it to Antarctica and rebuild it there. Now, we get to Antarctica in October, mid-October or late October, and the reason for that is because before that is 24 hours of night, so we need to wait until there's daylight there. And now the Antarctic vortex forms 4 weeks starting early December, and it lasts for 1 month, as I said. So from late October until, let's say, December 1st, because you want to launch as soon as possible to try to fly as long as possible, you need to put together this telescope again, working in the most remote and harsh place of the Earth, and be ready for launch in early December. So then you fly, if everything goes well, you launch and you're flying for 4 weeks. And now you have to land the telescope back on ice. And then you have to recover, but you don't know where. Well, you can more or less try to terminate the balloon in a convenient place. But sometimes, depends on how the winds are, that's not possible. So you need to go there with an airplane, try to investigate the area, and eventually land and try to recover everything and bring it back to the hangar. And you have to do all that process before sometime in February, where you're starting to get dark again. So the window is really, really small. So if you miss the window, you just have to leave everything there and come back the next year.
Oh no! and does it then have a like a sort of black box signal? So if it lands, in the wilderness, you can use a radio, like a radar, to find it.
We have GPS antennas because, of course, we need to monitor where the balloon is at any time during flight. So we know the position because of GPS, of course, within the precision of the GPS. And that's why you send first an airplane to the area to try to spot it. And then you just inspect the area, see where you can land, and then just go and pick it up. But yeah, we know the position of the balloon at any time after launch because of the GPS antennas, and of course, in terms of communications, we use satellite links to command the telescope because we can control. I said we cannot control where it moves, but we can control where it's pointed. So we control the telescope in real time, at least the pointing, and we receive the data also in real time.
I think it's definitely worth talking a bit more about the science that the telescope's going to do. One of the targets that I was reading that you're going to specifically be looking at is the galaxy Messier 83. Why did you choose the specific targets that you did in terms of the mission and science objectives?
So, well, the first reason of the targets is we are in the south sky, right? So we need to find targets that are in the southern sky and that are high enough so we can point it with the telescope. So because we have a balloon hanging on top, we have some certain operational limits. So we cannot point above 65 or 70 degrees. And then it depends where the targets are in Antarctica for the specific flight window that we have. So that's the reason in terms of logistics. In terms of science, we're looking for star-forming regions which are in different state of evolution, because at the end we want to analyze how the stellar feedback, supernovas and stellar winds, but mostly supernovas, reshape that gas that we're talking in the beginning to understand how it regulates star formation. So we want to do that in near targets. And one of the targets is Carina because it's one of the most active star-forming regions in our galaxy. So that's why we picked that one. And also because it's, of course, in sight from Antarctica. But we want to also compare with other places or other galaxies that can have star-forming regions with different stages of evolution and do that comparison or somehow those statistics that will allow us to constrain the models that we have for star-forming. So M83 was a really good target because it's a different state that, for example, Carina is visible, and also we're planning to do a whole map in high spectral resolution map of M83 that has not been done before. So it will be a very exciting science result if we get to do that map in both nitrogen lines and are able to understand because of that, the density of the ionized gas in that galaxy and compare it with, for example, Carina or other targets that are within our solar system. And that's the reason, for example, why we need to fly such a big telescope, 2.5 meters compared to much smaller in previous balloon missions. We really want to be able to have the sensitivity to look at the extragalactic sources like M83.
Will that map look like much to non-astronomers? Will it sort of be like a beautiful image that we can actually see, or is it more kind of scientific data that will only really mean something to astrophysicists and astronomers like yourself?
Well, that's probably a question to the scientists and see how they eventually put all the raw data together. But at the end, we're talking about nitrogen, but we will be able to see other lines, like ionized carbon, atomic oxygen, CO as well. So at the end, like any other mission, right, we're looking at wavelengths that our human eye cannot see, but this vibration of molecules, that is what we are trying to observe, we can assign a color afterwards and generate a map where each color is like a molecular emission, and it will be a three-dimensional map because we have this Doppler or velocity result observation capability where we can analyze how the gas is moving. So it will be a beautiful map, I think.
In terms of being at your most optimistic about the mission, are you sort of expecting to make real discoveries in terms of unlocking the secrets of stellar evolution and how stars are born and die and how they are reborn, I guess?
Well, I mean, that's probably a hard question to answer because every mission is a stepping stone, right? A step farther to complete our understanding of star forming in this case. So we're trying to complement data that has been observed before with other missions, like, we're talking about Herschel and inside Herschel instruments like HiFi and PAX, but also observation that have done with ALMA and with SOFIA. So the biggest thing here is that we're targeting that other nitrogen line, and the ratio between that line and another line that we can also observe at the same time with ASTHROS give us this 3D density of the ionized gas. And that is what we need to know to somehow improve the models that we have of star formation, because we don't understand really well yet. We know that supernovas and other stellar feedback control star forming processes. Because as I said in the beginning, otherwise all the dust would have been collapsed a long time ago and new stars wouldn't be forming, at least at the rate that they are still forming. So that piece of information is still missing. So if we get that with ASTHROS, we can put that in the models and basically get a little bit closer to a model that will allow us to reproduce star forming processes, which is, as I said in the beginning, is key for the evolution of galaxies and one of the biggest mysteries in astrophysics, still that galactic evolution. But there's another thing that we want to do as well as a target observation or target of opportunity observation, which is looking at protoplanetary disks in HD, deuterated hydrogen. So other missions have looked into protoplanetary disks to calculate the total mass of those disks where planets are forming around new stars. But with high-resolution observations like we want to do on ASTHROS, we can basically calculate the mass distribution to see how that mass is in the disk and basically understand better the process of new planets forming. It's not the baseline science of the mission, but it will be a nice observation to get to demonstrate that can be done, and then for future missions just have a targeted mission to do statistics of different protoplanetary disks.
Is there the possibility that you might actually be able to see the seeds of planets forming around the star?
I wouldn't say not directly, but of course if you can calculate the mass distribution, you can infer that something is going on, that a planet might be forming, just because you have that capability to measure the velocities and the mass and see where might be happening. it's not a direct observation of the planet forming. It's just an observation, as I said, of the mass distribution, and then you can use that as well to improve the models of protoplanetary disk and infer somehow what's going on in there.
It sounds like an absolutely fascinating mission, Jose. I just want to say, well, first of all, thanks very much for speaking to me today about it, but also just, best of luck with the mission and best of luck with the launch window. I hope you don't have to be in Antarctica for too long.
Well, I've been there for 5 months already in previous missions, so it's a wonderful experience. It's a very nice place to be. Not for so long, though, but it is an adventure. Definitely an adventure.